Hello everyone, welcome back to another video. Today we're going to be talking about linear regression. I'm Gus, and this is Endless Engineering, so let's dive right in. Okay, so let me start out by talking about regression. The idea of regression is that if you had a bunch of data between a dependent and independent variable, say for example you have the price of a house based on the square footage, or you have the miles per gallon by a car driven given its size or weight. And you want to predict that if someone came and told you, hey, I have this house of this size, or I have this car of this volume or mass, can you tell me how much I can sell this house for, or how much this house can go for? Or can you tell me how many miles per gallon this car can drive? So essentially the idea is you have a bunch of data and you want to fit a model to it so that you can tell in the future, predict based on that model what would happen. So let's take that as an example. So say I have some data, and we're just going to use generic labels here. Let's say I have a relationship between x and y, right? And I have a bunch of data here that says, okay, this relationship looks something like this. This is like real world data collected about these two variables that say, okay, this is how it looks like, right? So, okay, that's great. Now I know this data. And I want to say, okay, if somebody came and gave me an X, the volume of a car or the size of a house, I want to predict Y, right? That's essentially the whole idea about regression. That I would say that Y is equal to some hypothesis H of X and some parameters theta, right? Now in reality, there exists this function that is the truth, right? That says, oh, if I knew this H, the real H, and I knew the real values of theta, let's call them theta star, for example, right? Then I can predict exactly the value. But unfortunately, in reality, we can't do that. So all we can do is say, hey, y hat is some estimate with my hypothesis and my parameters that are not perfect, plus some epsilon, right? Where this epsilon is a small and acceptable error, right? Because you can't get it perfect. There's noise in the data, there's outliers, etc. Okay, so now this is regression. The idea that I have a variable that I can use to compute use the independent variable and some parameters to compute the value of this y, right? Now where does linear regression come into play? The idea that I can assume that my model is a linear combination of the independent variables. So let's say in this case, I look at this data and I say, oh, this data looks linear to me. That basically saying that I can fit a line through this data that captures it like this, right? It's not going to be perfect, but I'm going to estimate. Again, remember, we have a small epsilon error, right? Now this may not necessarily be linear data, right? This data could actually, look something like this, for example, right? So in this case, that looks more like a parabola, right? That looks more like something like that, right? So technically, I could still use linear regression for that. I could still say, oh, my model is theta 3 times x squared, right? And I can say that just because x squared is a term here doesn't mean it's not linear regression anymore, because I can do a variable substitution and I can call x squared b or z. So this can become something like theta 0 plus theta 1x plus theta, this is 2, theta 2z, right? Where I have defined z as x squared. I can still find a linear combination of these independent parameters. I can assume that x is independent, x squared is independent, and compute the value, an estimated value of y. Y hat is the estimated value of y. Now let me rewrite this in more of a vector format to make it simpler to look at. So if I write this as theta transpose x bar, right, where theta transpose is the row vector of theta 0, theta 1, theta 2, right? So now this could be theta n, right? There could be n number of variables. And x bar is 1, x, and z in our case. Again, this could be x1, x2, xn, right? So now this gives me my hypothesis. Okay, great. So now I know what regression means. Now I know what linear regression means. How do I get these theta parameters? That's the goal, right? We're trying to compute these theta parameters that tell us how our model changes based on the independent variable, right? So in linear regression, we define what is known as a cost function, right? J of x, theta, and y. And that is defined as following. 1 over 2m times the summation of I from 0, or 1, sorry, to m, y hat minus y squared, right? So this is my error term, how far I am from the actual y, and this is my, m is the number of data points that I have. So I have 10 data points, m is 10, so I'm summing over the entire data point, so I need to put a subscript I here, right? So every time I get an x, xi, the value of, x, z, whatever I have, I plug it into here, I get the y hat, and I know the y, the actual value from the data, so I get this error term. I sum over all of my data set, and I divide by 1 over 2m. This is a term just to normalize, because if you have a lot of numbers of data, you divide by the number itself, your cost doesn't explode for numerical stability. Okay, so the idea here is I have this cost function, and a cost function just tells me how much I'm penalized every time I change my theta, right? Because this cost has a theta in here, inside of this term, and if my theta is wrong, then I'm far away from this y, so this term grows, and then this squared makes it grow more, and the sum makes it grow more, so then my cost goes up. The idea here is I want to bring my cost down. And for a quadratic cost, which is what this is, so this cost basically looks something like this, right? It's quadratic. And its minimum is at 0, right? And 0 is when y hat is equal to y, right? If y hat is equal to y, I have perfect model, never happens in reality, and then that is equal to 0. And that's the goal here. So how do I do that? I do that with the gradient descent. So gradient descent is an algorithm that essentially computes the gradient of the cost. So the gradient of the cost with respect to the theta term, and you use that gradient to change your theta parameter. Let me explain what I mean by that. So let's say I have a value of theta here, this theta. Let's say I have some value here, so I take this value, I compute my y hat, given an input x, and I compute my cost, right? So on this plot here, I end up at this location with this cost. So this is given, let's call this theta 1, superscript here, so that we don't mix it up with the subscript. So then I compute the gradient here, which is the slope, essentially at this point. I compute the slope of this function here, and I know that that's the slope like this. I move in the negative direction of the slope. So I move this way, right? So in this case, I pick another theta. I mean, this is exaggerated at this case, but you get my drift. I have another theta here because I've computed it by moving along the negative of the slope, and I have my theta 2. I compute my cost at this theta 2. It's right here. And then I compute the gradient again, and in this direction, and I move downwards, and it's going to be a shallower gradient in this case. I will move closer, and if I keep doing that iteratively, I get to the minimum, right? And that's the idea here, that I can compute my theta plus equal to theta minus alpha times the gradient. Now, theta plus is the new value of theta. Theta minus is the current or old value of theta. And this is the gradient of the cost function. Alpha is a scaling parameter that dictates the size of the step that I take in the direction. And this is typically less than 1 for numerical stability, because if you make your step really large, sometimes you can overshoot and you end up here, and then you overshoot again, you end up here, you keep ping-ponging, essentially, and you never converge. Sometimes also if your step is too large, you go all the way up here on the parabola and you diverge. So your algorithm doesn't converge. Okay, so how do I compute this gradient? Essentially the gradient is if I take the derivative of this equation, right? So the derivative of j with respect to theta, and that's going to be equal to 1 over 2m. So this is a sum, that's fine, that stays here. I equals 1 to m. And then I take the derivative of a bracket is 2 times the bracket itself times the derivative of the bracket, right? So the derivative of y hat, which is from here, theta transpose x bar I, minus y hat I divided by d theta, right? And what's that derivative? That derivative is essentially xi bar, right? I end up with 1 over 2 and 2 cancel together, 1 over m, and I have the sum I equal to 1m times y hat minus y times x bar I, right? So this is the gradient of my cost. So if I take this gradient and I plug that here, right, then I have a recursive way to keep computing my theta and updating it and reevaluating my cost and then my gradient again and keep updating my theta until I converge, right? And the gradient descent algorithm can be generally implemented in two ways. There is what's called the batched gradient descent or batch gradient descent, and there's the stochastic gradient descent. For the batch gradient descent, in every iteration, we compute this sum over the data set and we keep updating theta. So it looks something like this. For my iteration, right, goes to max iterations, I do for sample of data, I compute what theta plus equal to theta minus, what do I have? Minus alpha times this term, right? Delta j. So in this case, you can see that in every iteration, I have to compute the sum over a large data set, right? And if I had 100 iterations and I had 1,000,000 points in my data set, then I would have to do a lot of computation. So you can see how this can become unattractive for large data sets. So this is the batch gradient descent. However, for a stochastic gradient descent, what is done typically is we shuffle the samples. So the first step is to shuffle randomly. So that way all my data is shuffled randomly and I pick the data points randomly and I do for sample in my data set, compute the update of theta. Right? So this is the stochastic gradient descent algorithm. So there you have it. Regression is the idea that I can come up with a hypothesis that allows me to predict the value of a dependent variable given an independent variable. So this, in this case, y given the value of x. To do that, I make a hypothesis about my relationship. In linear regression, it's assumed to be a linear combination of these variables. Here we have theta 0, theta 1, theta 2. These are my parameters that I need to compute in x and x squared, or z in this case. So that's my hypothesis right here. I formulate the problem as the minimization of this cost function, which is the sum of the squared error, right? This is my hypothesis and this is my actual value, and I take the sum of the squared error. And to do this, to minimize this cost function, I use the gradient descent function. And that essentially tells you that to update your parameter value, you compute the gradient of your cost function and you update it by moving in the negative direction of the gradient. That way you go to the minima of your function. And in this case, our function is quadratic and nice. It's not always like that, but in this case it is. We move down to the global minima, or 0. And in that case, we never actually get to 0, but we get as close as possible, and we have our theta parameters. And we can do that in gradient descent in two different ways: the batch gradient descent and the stochastic gradient descent. Each has their strengths and each has their weaknesses. It's up to you and based on your problem or based on your data set to pick the right one for you. Another way to look at the linear regression problem for solving for theta, we can use the least squares approach, or the linear least squares approach. Some of you might have heard of it, so let's see how we can use it here to get an analytical solution for finding the parameters theta in our hypothesis, right? So given this hypothesis, where y hat is theta transpose x bar, like we define theta transpose to be this row vector and x bar is this column vector, then let's say that given all my observations, I have m observations, I create this matrix capital X, and that's going to be x1 transpose bar, x2 transpose bar, all the way to xm transpose bar, right? And this is a matrix that's in the m by n space, right? Where n is the number of variable parameters theta that I have. And let's say I create this capital Y matrix, I stack up all of my Y values. So this is going to be y1, y2, all the way to ym, right? So this is a vector in m space, right? And my theta is a vector in m space as well. So I can define my cost, function of theta x and y, capital X and y, as 1 over 2m times x theta minus y transpose x theta minus y, right? This is essentially equivalent to the cost that we defined earlier, which was j is equal to 1 over 2m, summation of I equals 1 to m, theta transpose xi minus yi squared, right? These two are equivalent, okay, because this sum is taken care of by all these matrices. So when I look at this and I want to minimize this function, right, what do? I take the derivative of this function with respect to theta. That's my parameter that I want to change. And what's the derivative of this right here? It'll be 2 over 2m times x theta minus y transpose times the derivative of this, which is x, right? This 2 cancels with this 2. Now in order to minimize this function, I take the derivative and I set it to 0. And if I take that derivative and set it to 0, I can then say that x, let's expand this transpose here and multiply in the x. So when I take this transpose and I put it in here, it becomes theta transpose x transpose, because these flip order. And then I multiply them with x, and then I subtract capital Y, sorry I keep messing it up, transpose times x, and that's equal to 0. This m goes away with the 0, right? It doesn't matter. So from this equation, I can then solve for theta itself. If I take the transpose of this equation and take this side, take this term to the other side, so we get, let's take the transpose first. You get x transpose, you got to flip them. X transpose x theta is equal to x transpose y. And then I can solve for theta by inverting this term right here. Theta will be equal to x transpose x inverse x transpose y. So that solution comes from the linear least squares, or LLS, right? The linear least squares approach is I take my problem of linear regression, I then stack all my observations into these big matrices, x and y, and I formulate my cost in this linear algebra way of matrices rather than this summation notation. And then I take the derivative of this cost and I set it equal to 0. And when I expand out the terms that I have here, I end up with x transpose x theta is equal to x transpose y. And I take this value and I invert it. Hopefully that value is invertible. That means you have a data set that is, rich and you can invert. You can compute your theta this way. So this is an alternative to using the gradient descent method. Now, sometimes this matrix is non-invertible, and there's other algorithms such as the Levenberg-Marquardt algorithm, which adds a term in here that makes it invertible. Let's not get into that. I just wanted to show you that the same problem can be solved using the linear least squares approach, or the idea really of optimization, that I have a cost function and I'm trying to minimize it, and I do that by taking the derivative and setting it equal to 0. It gives us this nice equation, which is the linear least squares, to compute the parameters. And it should give you an identical solution to these gradient descent. Well, not identical, but it will be close enough, essentially, because the gradient descent is iterative, right? And based on how your cost looks like, it will give you different solutions. It'll be close, though. But this is an analytical solution to the problem. If you like this video, please hit the thumbs up button. And while you're there, think about subscribing to Endless Engineering so you can support the channel. Thanks for watching.